Hello everyone and welcome back. In the previous video, I explained the connections of the right part here. R1, R2, ALU and also the bus to communicate between these two parts. If you look at the circuit, this is our bus, this is the ALU. Let's say this is R1 and this is R2. I removed some wires from here because I'm going to do some modifications. What I want to mention here is, in the previous video, we focused on the addition operation. Today, we need to extend this circuit to include the subtraction feature or the subtraction operation. We are doing this because by the end of the course, we need to write assembly code that can run multiple operations, not only the addition operation. How can we add the subtraction operation to this circuit? To do so, let's start with some theoretical explanations, and then later on we can move to the hardware implementation. First of all, I want to discuss with you the negative numbers. How can we represent the negative numbers? We have three methods. The first one is called like sign method. I don't remember the name anyway, but it is very easy because all you need to do is to reserve the left bit, the last left bit, to the sign value. Let's say, for example, this is 11000. So this is called positive 3, right? You know how to convert from binary to decimal. 1, 2, these are the weights, so 1 plus 2 is equal to 3. If you want to represent negative 3 using the first method, all you need to do is to write everything as it is, except the last bit on the left, you need to write this as 1. So this is negative 3. This is for the first one. And by the way, I am not explaining many examples. I am not focusing on the details because here this is not a digital design course. I'm just focusing on the CPU design. And if you missing anything here, you need to search on YouTube for more details. The second one is the ones complement. This method is very easy also. Let's take the same value here, 11000. All you need to do is to just negate all the values. Convert the 1 to 0 and the 0 to 1. So it is gonna be 0, 0, 1, 1, 1. So if this is positive 3, this is gonna be negative 3. The third method is called 2's complement. The 2's complement is similar to the first complement because it just takes the first complement and add 1. So let's say this is 11000, positive 3. And by the way, if we look at the positive values, they are the same in all cases, in all methods. But for the 2's complement, you need to add 1 here. So 0 plus 1, it is gonna be 1. And these values will be the same. So this is negative 3. That is all you need to do, all you need to understand now. But for the 2's complement, I need you to write the 2 steps. First step, use the first complement. And the first complement means negation. Negation or negate all value. Number 2, add 1 to the value. That is what we need to do. So this is the first theoretical part. Let's discuss another theoretical part, but don't forget these 2 steps because these are the theoretical steps and I am going to show you how to implement these theoretical steps by the hardware. So let me remind you with the XOR gate. Do you remember the truth table of this gate? Let me write the truth table. Let's say 0, 1, 0, 1, 0, 0, 0, 0. And let's say this is A, B, and C. So they are, the values will be 0 if they are similar and 1 if they are different. This is how the XOR works. Now I have two equations that we need to understand. The first equation is if we take any value, let's say x, and XOR this value with 0, what will be the result here? So to understand the result here, you need to use the two combinations of the x value, 0 and 1. So let's assume that we here use x is equal to 0. Then the value will be 0 XORed with 0, and you can see from the truth table 0, 0, 0. And then if x equal to 1, then it is gonna be 1 XORed with 0, which is equal to 1, because this is 1 and this is 1. My mistake. So 1 XORed with 0 is equal to 1. So 1 XORed with 0, it is equal to 1. So that means if you look at the x value on the left side, 0 becomes 0. 1 becomes 1. So if it is x, it will be x. That means x XORed with 0, it is gonna be x. That is the first equation that you need to understand. The second equation is x XORed with 1. Let's take the same scenario. X is equal to 0, x is equal to 1. So 0 XORed with 1, the 0 XORed with 1 equal to 1. And then 1 XORed with 1, 1 XORed with 1 equal to 1, 1 equal to 0. I need you to look at the x value, the value on the left side. So if you look at the value on the left side, it was 0, the result 1. It was 1, the result 0. So if it is x, the output will be x bar, right? So this is gonna be equal to x bar. So these are the two equations that you need to understand. This is the first and this is the second one. I am explaining this because if you look at the first step here, we said that the first step is to do negation, is to convert the 1 to 0 and the 0 to 1. That's okay because we have this equation. If we have x is equal to 1, it is going to be 0. If it is 0, it is going to be equal to 1. That means we can use this circuit like this. Put 1 here and any value, any number here, and the output will be this value. So this is the first complement. And if we replace the value 1 with 0, the output will be x, not x bar. But I need to focus on this now. So why I'm explaining all of that? Because let's take an example. It is gonna explain everything. Let's say that we have a value equal to a. Let's say 1, 1, 0, 0. And b equal to, let's say 1, 1, 0, 0, 0. And we need to calculate a minus b equal to what value? So this is 3 in decimal, this is 1 in decimal, so we know that the result will be 2, right? So it is gonna be 0, 1, 0, 0. This is our result before explaining anything. But we need to apply this theoretically and also by the hardware. How can we do this? All you need to do is to just say b, this is 1, right? So we need to get minus 1. This is b, and we need to get minus b. How can we get minus b? By doing the 2's complement. So the 2's complement consists of 2 steps. First step is to do negation. So it is going to be 0, 1, 1, 1. Second step is to add 1 to this value. So the value will be 1, 1, 1, 1. So this is equal to minus 1 using the 2's complement. So what we need to do is to say a minus b is equal to 1, 1, 0, 0. This is a. And minus b is equal to this value, 1, 1, 1, 1. You need to add these two values. So it is going to be 0 plus 1, 1, 1, 0, 1. This is 1. And this is, this is 1. we are adding, right? So yeah, this is 0 and 1, and this is 0 and 1. For now, I am going to neglect this value. And as you see, this value, the output here is equal exactly to this value. I'm not going to explain why we neglect the carry out for now, but as I said, this can be found in the digital logic design course. But if you look at the first 4 bits, you can see that we have 2 as we expected. So what we need to do now is to implement this in hardware. So we know in the hardware we have a 4-bit adder, 4-bit adder, and this adder takes 2 values, A and B, and it provides one output value, let's say C. So I am going to say this is A0 and B0, A1 and B1, A2 and B2, A3 and B3. So the values of A and B, if you remember, I'm going to write them here, 1, 1, 0, 0, and B is equal to 1, 0, 0, 0, and minus B is equal to 0, 1, 1, 1. So it is equal to 1, 1, 1. These are the values from here. So A is equal to 1, 1, 0, 0, 1, 1, 0, 0. B is equal to 1, 0, 0, but we are not dealing with B because we need negative B, so I am going to use this value instead. Once you use -1, you can add A plus minus B, so A plus this value. So what we need to do is to write the A values as it is, because we are not negating or trying to obtain the 2's complement or anything. So I'm going to write this value, because this is A0, this is B0, A1, B1, A2, B2, A3, B3. So I'm going to write this as 1, 1, 0, 0. That's it. For B, we cannot say that, because B itself is 1, 0, 0, 0. But the value that the 4-bit adder should receive, it is not 1, 0, 0, 0. It should be 1, 1, 1, 1. So we need to add these values here, 1, 1, 1, 1. But in the program, in the assembly language, the value was 1, 0, 0, 0. And the output that we put here is 1, 1, 1, 1. So we need to add a hardware circuit here that takes this value and provides this value. That's what we need to do. If you remember, for the 2's complement, we do 2 steps. The first step is to do the first complement, right? So I am going to write here B, and the output will be B bar, and put here 1. So I am going to come to each one of these B values and write here B. This is B0, B1, B2. I mean like bit 0, bit 1, bit 2, and this is bit 3. And then all other pins for each B bit is gonna be 1. So I am going to do like this. And I am going to add here 1, right? So let me ask you, this value will be 1. So 1 XORed with B0. What will be the value, the output? 1 XORed with B0. It will be B0 bar. So if B0, this value, 1, if this is 1, the output, the output will be, the output should be 0, right? This is a problem, but I'm going to explain why it is 1, not 0. Okay, so, it should be 0. Yeah, it should be 0. And then this value is 0. It is 1, 0. It is 1, 0. It is 1. Now we have the first problem, because this value is 0, right? But it should be 1. That is because we didn't do the second step. Because let me take this value, B here. b is equal to 0, 0, 0, 1. The first step is to do negation, right? So it is going to be 0, 1, 1, 1. But this is not the 2's complement. This is the first complement. So if you want to do the 2's complement, you need to add here 1. So 0 plus 1, it is going to be 1. That's why we need to add here 1. How can we add here 1? You know that the 4-bit adder has a carry in here. A carry in here. So if you put the carry in 1, that means that you add 1 to A0 plus B0. So A0, A1, A2, A3, B0, B1, B2, B3. If you do subtraction, you need to add 1 here. That's why we're adding the carry in here, right? This is our subtraction circuit. So here I want to ask you, this is a subtraction circuit, but how can we do addition, not subtraction? Because the 4-bit adder main purpose is to add, not subtract, but we added this area to make it do subtraction. To do addition, all you need to do is to take this value and put 0. If you put 0 here, the value will be exactly B0. Because, do you remember this value? If you put the value XORed with 0, it is going to be the same value. So B0 XORed with 0, it is going to be B0. It is not going to be B bar, okay? It is going to be bar if it is 1. It is going to be B0 if it is 0 here, right? So that is how it works. If you put here 1, the value here will be the first complement plus 1 from the carry in. If you put 0, the carry in will be 0. So we're adding 0 here instead of 1. And also all values here will not be negated, and it will be the same here. And if they are the same here, then this is going to add A to B, not A to the 2's complement of B. So that is our circuit. I think that's enough for this video. I don't want to make the video too long. But in the next video, I'm going to implement this circuit in hardware. So you will need to watch this video to the end. And that is all for today, and see you in the next video.